Come in, come in. Welcome to the tutorial session. Settle down. The Wi-Fi password is Cosyne 2023, small caps. I think we're going to wait a couple more minutes for more people to come in. For people outside, come in for the tutorial. All right, let's get started. Hello, everyone. My name is Meming Park. I'm the backup tutorial chair of Cosyne tutorial. Welcome to the tutorial session. It's wonderful to see all of you here. Yes, please settle in. There are plenty of space here. Plenty of space in front. So today we're going to have Kim Stachenfeld to talk and tell us all about reinforcement learning. I'm not qualified to introduce her quite well, so she's going to introduce herself. So here you have her.
Everyone. Can you hear me okay? I can hear myself quite boomingly, so I assume I'm propagating through the room. I am Kim. I'm going to be giving the tutorial today on reinforcement learning. Before I introduce myself, I'm going to introduce my magnificent TAs, who are Ching Fang and Tom George. They're both PhD students at Columbia and UCL, respectively. You can find them over there, and when we get to the coding section of the tutorial, they'll be circulating and able to help out with the code. So I wanted to give kind of a little bit of a quick overview of who I am, so you know who's telling you these things and kind of what I know about what am I not. So my background, far back in undergrad, I did chemical engineering and math. And then I went to grad school in neuroscience, like probably a good fraction of you. I, in grad school, researched how the brain constructs predictive models of related states for efficient reinforcement learning. So that was sort of my intro to reinforcement learning, was in grad school and using it to model animal behavior. And then I went to DeepMind, where I currently work. And I'm working on both some neuroscience problems. That's the self loop. I'm still working on problems in that space. Turns out there's a lot of them. And I'm also doing some machine learning problems that also relate to this problem of how we can learn structure about the world and use it for reinforcement learning. So kind of my view on these problems, the field that I've really dove into the most, is representations of structure of the world and how that makes reinforcement learning easier. First, we need to talk a lot about what reinforcement learning is and what the problems are with it. And probably a bit of this tutorial will be magnified towards some of those like structure, model, and representation problems than a different RL speaker would have. So first, to start out with the very essentials, what is reinforcement learning? So the reinforcement learning problem is this one. You want to learn a policy for selecting actions to maximize total expected reward over future states by trial and error. This is a pretty general framing of a problem. Just try stuff. See if it was good. If it was good, do more of that. Try to pick actions that make things better. Its generality means that it can be applied to lots of different types of problems. You can apply it to games, problems like chess, where your state is the configuration of pieces on the board, and you want to maximize, eventually, your probability of winning the game by selecting good actions. You can apply it to navigation problems, where your state is a location in some environment, and you, this rat, want to maximize the number of Fruit Loops you get. You can apply it to control problems in robotics, like figuring out how to move your arms and legs if you're this little like cartoon two-dimensional cheetah creature. And you can apply it to problems like trying to make a baby laugh, something very naturalistic and real world, where you get a little shot of dopamine if you succeed in making your friend's daughter chuckle at something amusing. I think in this case, I smelled her feet, which is apparently something that babies think is hilarious. So reinforcement learning is typically contrasted with these other types of learning. And I think my favorite example to kind of illustrate all of them is to just imagine you were trying to learn biology. This is something many people in this room have probably tried to do before. Unsupervised learning on the far left would be learning patterns or structure in the data that you're encountering. So maybe you try to read a bunch of biology books and you write diagrams that capture the structure of biological processes in low dimension, or you build a text model that produces sentences that are generally accurate about biology. That would be unsupervised learning. You're not trying to ace a test or solve some problem necessarily, just try to capture patterns. Supervised learning is more directed. Here, there's a notion of a right answer, and you're trying to learn how to produce that correct answer. So this would be like learning biology by taking lots of multiple choice tests on biology and trying some answers, then getting a scorecard that says what the correct answers were, and then modifying your strategy for picking multiple choice answers to questions in order to maximize your probability of getting a green check mark. In reinforcement learning, you learn from a scalar reward signal that just says it monotonically increases with how good the actions you took were. So that would kind of be like trying to learn biology by taking a test and then just getting 33 back as the answer. You don't know what it's out of. You don't know if it's out of 33 or out of 100 or out of 1,000. You don't know which questions you got right and which questions you got wrong necessarily. You have a complicated problem with figuring out which actions you took were actually responsible for whatever reward you got at the end, whether that reward was good or bad. This is kind of a setup for this challenge of trying to learn autonomously in the world when there's maybe a notion of better or worse, but not a notion of a correct answer or an incorrect answer. And I think one thing I like about this example is I think it illustrates that reinforcement learning is quite hard and doesn't really help you out very much. I think I often, at least when I started, I kind of intuitively thought of reinforcement learning as something quite warm and fuzzy and friendly, like, oh, you did a good job, you get a cookie, like, what a lovely system. But actually, I now think of reinforcement learning as kind of like cruel and passive aggressive. And I think that's really the right intuition to have and really illustrates why reinforcement learning is so hard, that you just are left to figure out a lot of the problems for yourself. This is also why it's a good fit for modeling some of the challenging problems of autonomous learning in the real world. I also want to just quickly mention when people use the term reinforcement learning, I think it can refer to two different things. Sometimes it's talking about a problem itself, the problem of learning from reward, and sometimes it's talking about a batch of methods that are typically used for RL problems. And it's good to know the difference because sometimes there's things like, oh, we used this thing that we didn't think could be used for RL. And you're like, wait, was that RL or not then? And I think it can be a little bit confusing, and just know that there should be a bit of a bimodal distribution over its usages, even when I'm talking, because I'll probably forget to be super clear in every slide. Okay, so the reinforcement learning framework consists of two main parts, an agent and an environment. We can consider these just functions in the computer science sense or math sense, where the agent takes in an observation and takes in reward from the environment. It updates its state, and it outputs an action. The environment is something that takes in an action, updates the environment state, and then outputs an observation or reward. And so these things exist in loop with each other. The agent taking in observations and rewards and giving out actions, and the environment's taking in actions and updating its state accordingly. The typical components of an agent are these ones. There's the state of the agent, which depends on the sensor, on its incoming observations and the history of observations that it's seen. There's the policy, which is usually called pi, which is a map from the agent's current state to some action, or more commonly a distribution over possible actions. It might have a value function. In most of the methods we talk about, it has some estimate of how much reward it thinks it's going to get. This is a very useful thing, but actually is technically optional. And it might have a model of the environment, some sort of theory of how the environment is turning its actions into observations and rewards that it could use for reasoning. This is also optional. So for the outline of this talk, I'm going to start with talking about some RL fundamentals. If you guys already know some RL stuff and are really here more for like the deep RL or the special topics, more new stuff, you will find this very boring, and I won't be sad if you go to get a glass of water or a cookie or some coffee or something. I'll then talk about model-based RL and some of its neural analogs. And then I'll talk about function approximation and deep RL. And then at the very end, I'll talk about some philosophical musings. These are really meant to seed discussion topics for the break or perhaps for the end of the second stage of the tutorial, depending on how we're doing on time. So to start off, in the beginning, there was Pavlov. And basically, you've definitely heard of this. Pavlov presented some meat to dogs, and whenever he did that, he also played some tone, and then he noticed that whenever he played the tone, the dog started to salivate. And this demonstrated that animals can learn an association between an unconditioned stimulus and a conditioned one. The unconditioned one is the one that gives them some sort of reward regardless of the associations they've learned. The conditioned is the one that requires Pavlovian conditioning in this case. So if things happen at the same time, an association is learned. That's pretty elemental. But it turns out it's not just co-occurrence that matters, expectations matter too. And this is sort of the beginning of moving from that basic association to the reinforcement learning, the rest of the reinforcement learning paradigm. So what blocking means is that, let's say in phase 1, you just do Pavlovian conditioning. You've got tone, and then in this case, you've got cheese. And then in phase 2, you add a new stimulus, maybe a light. And you play that at the same time, so now light and tone could both be associated with cheese. At test time, you just show them the light. And you say, do they show some indication that they're expecting cheese now? Does anyone have a theory? Just shout it out. Okay, all good theories, it turns out, because experiments were needed to show that no. It turns out the light does not get associated with the cheese. And the reason is because that there was no surprise. Once they learned that tone predicts cheese, there was nothing surprising about the fact that cheese happened after a light because the tone was there to explain it. So it's not just the stimuli co-occurring with a reward, it's the fact that it's occurring with an unexpected reward, that it's required to explain this surprising reward that wasn't necessarily predicted. So the next computational model that was introduced to start explaining this is Rescorla-Wagner. And this is a simple model of how animals can learn expectations about upcoming reward. So just to break down this equation, delta V is going to be the change in the expected value. Alpha and beta refer to the salience of the two stimuli. Basically, if the animal doesn't notice them, it's not going to learn about them. And then this difference is defined at the bottom. Lambda is the actual reward, the value of the unconditioned stimulus, which is 0 if it's not there and 1 if it is. And then the sum of the V's is basically the sum of the expected values that are coming up. So if the actual minus the expected is 0, nothing is learned. And if actual minus expected is something, then delta V, the amount that you update your value expectations by, is some number, and you change your expectations. So we can apply this in the context. So this is actually, So this is all about how to learn about rewards that are just happening to you, rewards that you have no role in, your choice has nothing to do with. But of course, what we really want to do is start using these predictions in order to make choices. And we can do that in a simple setting with Rescorla-Wagner and actually start to see the complexity of the problem in the case of n-armed bandits. So this n-armed bandits is based on a joke that slot machines are armed bandits because they have this arm that you pull and they take your money. You shouldn't gamble, obviously. And in this case, you basically have the choice between these two slot machines, and you want to decide which one you should play next. Of course, the answer is neither because gambling is not a good idea. But let's say you pick arm 1 instead, and you get $1, and you pick arm 2 and you get $0, and you pick arm 1 again and you get $1, and so on. And you start to get a pretty good sense of the profile of possibilities from these different options you have available. We can plot the expected value for both of these arms, which if you're a data scientist or neuroscientist, it might be the thing that you want to do next with it. And then you use this to try to answer the question, which arm do you pick next? And I think most people would probably pick arm 1 because the bar is higher. I certainly would. Sorry, these are just going a little slow. And there's a decent chance that you'll get reward because you usually do with that arm. But of course, there's also this possibility that there could be a really unlikely but very high value associated with arm 2, and you won't know this unless you pick arm 2. So this illustrates the explore-exploit trade-off, which is that if you pick the option that you think is the best right now, you rule yourself out from exploring this option that doesn't seem like the best right now, but actually could have some hidden reward associated with it because you're just not 100% sure how to relate the past to the future. So there are a number of ways that you can start reasoning about this explore-exploit trade-off. This fact that in order to try and get the most that you can based on your current expectations, you have to forego learning other options. The simplest one, and one that's going to come a lot in the rest of this talk and also in the tutorial, is epsilon greedy. Epsilon greedy just means that most of the time, a fraction equal to 1 minus epsilon, you're just going to take the action that you think is the best. You'll pick the action that has the highest current value. But epsilon of the time, maybe 0.1, maybe 0.2, maybe 0.5 of the time, you'll just pick a random action. And that way, you won't only be picking the actions that seem best right now. You'll also have a little bit of jitter for these other actions. And if they turn out to be really good, you have an opportunity for their value to go up in your estimation. A slightly more sophisticated version of this is something called softmax. And here, you're choosing actions according to a softmax function, which makes valuable actions more likely, but it doesn't make their likelihood deterministic. It basically is kind of a relaxation of your greedy function, such that if you have estimates for different options, things that are more valuable are more likely to get picked, but you're not completely indifferent among all of the other options besides the most optimal one. Their probability is weighted by how valuable you think they are. And both of these are kind of on a scale from completely greedy to completely random. And in the case of epsilon greedy, the parameter that governs this is epsilon. If epsilon is 0, you just pick the greedy action. And if it's 1, you just randomly act in the world. In softmax greedy, you have a beta parameter that also moves you on a scale from completely deterministic to completely uniformly random. And here are a couple lines showing for these 10-armed bandits, if their values kind of drop off smoothly from right to left, how you would pick them for different values of these parameters. There's also a couple of other fancy ways to try and balance your explore-exploit trade-off. One of them that I think is particularly evocative is just being optimistic at first. And this means that any interactions with the real world will lower your expectations, meaning you get sort of a bonus to things you haven't tried that much yet. Kind of as some sort of lesson, but I'm not quite sure what. And then upper confidence bound is basically estimating a confidence interval as well as your current estimate. And instead of using the expected value, you use the expected value plus your confidence interval just to give it the benefit of the doubt. It's also kind of a version of optimism. There's also a couple of bandit variations that you might want to know before we move on. These are surprisingly useful and expressive frameworks for exploring different types of reward paradigms. You have drifting bandits where the rewards drift over time if you want to study how people or animals continually learn. Contextual bandits where the best option depends on your context. And correlated bandits where there's hidden underlying structure that links the different bandits that you could try and probe how people know. So bandits are already fairly complicated, but of course they are simple in one main dimension, which is that they have no structure over time. And most of the RL applications that get really, really exciting have some structure over time. And the way that it's typical to model this is using something called a Markov decision process. And a Markov decision process features elements that will be familiar to you from our sort of introduction of what an environment is. It has states in it. It has actions that you can use to transition among the states. probabilities of transitioning associated with those actions, and reward at each state. And gamma here I'll get to in a bit. So the Markov property is basically a simplifying assumption which says we're going to pretend that your future only depends on your current state, not at all your history. This is a really important assumption. If every prediction you made depended on your entire history, you could literally never be in the same place more than once. Because your history is always changing. It's always adding this current moment to it, and then the one after that, and the one after that. There's never this feature where you can go back to the same place. You also have a very, very, very large state space to learn about of things that don't repeat each other if you're trying to learn about your entire history's relationship to reward. So we're just going to pretend that your current state has all of the information relevant to predicting your future. And this is a good assumption for a lot of cases. If we want to try and figure out where I'm going to walk to in this room, you probably don't need to know what I had for breakfast yesterday, or you probably don't need to know that I'm from New Jersey. That's probably not going to be relevant to predicting the immediate future, although who knows, us New Jerseyans can be really unpredictable. So to illustrate a Markov decision process, I have an example that I borrowed from Jacob Bakermans and Tim Behrens. And I mentioned that I borrowed it for them for two reasons. One, to give credit where it's due, but also to kind of distance myself from it because it paints a slightly bleak picture of life and research. But it's perhaps one that would be uniquely relevant to an audience of researchers. So we're going to construct an environment where there are a set of states we can be in, a set of actions we can take, whether to apply for a grant or write a paper, transition probabilities that move us through this state space, and a reward function, which is going to be, in this case, getting a grant. So we start off in the world of research, poor and unknown. At this point, we have the option to apply for a grant or write a paper. And you might say, Kim, you work at DeepMind, you don't apply for grants, which is true, but I do need compute. So you can just replace grants with GPUs and get something that applies more broadly to researchers. So if I try and write a grant right now, I'm probably not going to get it. I don't have any papers yet. So let's say I try to write a paper. There's a good chance I'll try something and it won't work because science is hard. But let's say there's also a probability that I will write something that works really well, and then I become grantless but famous. Just takes one. And then I can continue to take actions that will move me through this world in different ways. Maybe now if I apply for a grant, I have some chance of getting it because I'm famous. Or maybe I will apply for a grant and not get it and just remain poor and famous. If I write a paper right now, I'll probably stay where I am because I can't get a grant from writing papers at this point. So if I keep taking actions, I can keep moving around this space. Every action is associated with some risk. The transition probabilities are stochastic. In this case, a design choice, which simplifies the problem, was made to treat getting a grant as reward. But that itself is a choice of the environment that people could question. Maybe we just get grants to write papers, or maybe we just write papers and get grants so that we can hang out in the neuroscience building and drink coffee. All of these are possible valid choices of reward, and that the designer has to pick this is kind of a major assumption in RL. Just to kind of preview the example we'll use for the tutorial, if we were to use a grid world, an incredibly common environment for starting to reason about RL problems, then our set of states would be these little squares. Our current location would be given by the location of that slightly creepy smiley face. The G, the goal, denotes where there is reward, and actions will be up, left, right, down. So to start reasoning about these problems, we're going to introduce state value functions. So I probably said a couple times now, really quickly, the phrase expected future reward. And that is what value is, and that's what we're going to try to optimize. So in this case, we're considering the value of a state, and the value of some state in our environment is going to be equal to the expected future reward over time. This summation is over future time. Gamma we'll now get to. Gamma is a discount factor, which is used to prioritize immediately upcoming rewards over distant future ones. So gamma is less than 1, and it just says, I care more about reward today than I do tomorrow. This is a psychologically plausible assumption, it's also just really important to getting anything to work. There's variants that get away from it by using like the expected rate of reward rather than discounted reward, but this one just tends to be a lot more popular and useful. OK. Oh, I forgot I had these coming in. OK. So we can break this term down by pulling out the first reward at time 0 and putting the rest into a recursive summation of the same form. And because when we pull out the first one and leave the rest intact, we still have a discounted summation over future reward, then we can actually just replace that second summation with the value of the next state. So this basically means the value of my current state is equal to the reward I will get now and the value I'll get at the state after that. The state after that is kind of keeping track of what the value is that you get later. And this recursive formulation of value is called the Bellman equation. And the fact that you can phrase value recursively is going to be really important for when we want to start evaluating our actions, our current value function, and also updating it. So what TD learning does is basically continue to modify your estimate for this value function using surprise. So VT+1 is going to be your value estimate next, and you're going to update it with your current value estimate and however surprised you are. So this delta here, that's the difference between what you expected and what you actually got. That's going to be your surprise or your temporal difference. And the eta next to it is the learning function. Oh, I actually have text coming in that can explain these. So this will be your new estimate of the value, your old estimate, and the prediction error you get about upcoming reward. So this R plus gamma V is going to be what you actually observe, the reward you get, and then how good the state you get to next is. And you're going to subtract it from your previous estimate. And if you continue to update your value function in this way, you'll eventually, through painstaking exploration of your environment, get a decent value estimate for the expected reward that comes after each state. So this is sort of this reward prediction error is the basis of the dopamine reward prediction error hypothesis. And this is basically the hypothesis that what dopamine is encoding is equal to this reward prediction error, and that it's used to continuously update your expectations about how much reward is going to happen. So the key experiment that started this all was Schultz, Diane, and Montague, a very famous one. And basically what they found is that if you give a monkey some reward, then this evokes firing in the dopamine neurons. And if you then do a conditioning experiment where they encounter some stimulus that's consistently predictive of the reward, then eventually you start seeing dopamine fire after the conditioned stimulus and not at the reward. But if the reward that's predicted is absent, you actually get a decrease in the firing of dopamine neurons. So this is very consistent with dopamine neurons encoding a surprise about reward based on their expectations. And there's been lots and lots of modifications of the dopamine reward prediction error hypothesis. It's been modified in several ways. It's been challenged in several ways. I definitely did not list all of them. And it's a very active field. If you're in it, it's honestly pretty exciting and interesting. But I'll just kind of leave it at this for now. OK, so we're now pretty good at trying to estimate how much reward we're going to get in the future, but we still haven't actually done anything to modify our actions. We're still just kind of sitting there, letting time pass, letting rewards happen to us, and trying to make expectations about how much reward we're going to get. So now we're going to start improving the policy and changing how you're taking actions. So this was the way that we're updating our equation before. This is taking our previous V and modifying it by our prediction error and getting a new estimate for V. It turns out we can make a really simple substitution for this and make this an equation that changes over time and starts getting closer to what the optimal value function is. The optimal value function is the one that happens if we're taking the best possible actions. So the key difference is just this term here. We're going to take the value of the maximum action rather than the one that actually happened. And an important thing here is we're also starting to separate out our value into not just a function of state, but a function of state and actions. So we're going to keep track of the value not just of a particular state, but of the value of a state and the action we took there. And multiplexing our value function in this way will allow us to choose actions that are valuable rather than choosing states, which isn't really something we have control over. Cool. So we're going to very similarly update our new estimate for Q based on this modification using a Q learning prediction error rather than the TD prediction error. And this is useful for finding what we'll call the optimal policy. So what I just described was how you find the optimal value function. And the way you can turn this into actual behavior is to just consistently pick the action that's most valuable to you. So this might seem kind of obvious, but there's actually some variants on it that start to get pretty interesting. So basically, this method is just keep learning the value of every action and then pick the one that seems best in any current moment. And kind of the interesting thing about this, and the thing that maybe seems kind of intuitive, but actually isn't mathematically obvious, is that if we keep alternating between these phases of evaluating your policy and improving your policy, evaluating what your Q looks like and then improving it, we start to move towards the optimal value function and the optimal policy. So basically, you can evaluate how good your policy is by estimating what the current value function is, and then modify it by selecting the maximum action to replace this with. The other thing is, I mentioned explore exploit before in the context of bandit problems, which is a good place to visualize them. But just to mention that this problem gets much, much, much harder in temporally extended environments. So this is basically hard because random actions don't necessarily give you very good coverage. If I kind of randomly sample from the actions that are available to me, I'll kind of just wander all over the place and cross over the same territory a lot. I'm not really encouraging myself to cover anything new or do anything different. Random walks are basically really tough policies to explore the environment with. There's a lot of work on trying to make exploration policies more sophisticated, which I'll talk about in the next slide. But basically, like the challenge is that if you just randomly pick from the actions you can see right now, they're not actually very likely to cover your environment ultimately. So what you have to do is something that is called deep exploration. And the asterisk here is to denote that this is not deep as in deep learning. This is deep as you go in the same direction for a really long time. And this is to kind of avoid the dithering that random walks give you, where you cross over the same ground too many times. So one policy for this is something called Thompson sampling. This is kind of an interesting one. You choose optimal actions with respect to a randomly drawn belief. So I just say, like, I'm going to pretend over there is super rewarding, and then just use normal RL to pick the optimal actions. And picking rewards at potentially faraway places means that you're going to explore your environment more thoroughly. There's sampling distributions that give you better coverage. So if you want to use something kind of like a random walk, but where you end up going really far away every once in a while, levy flights will do this. You can use uncertainty-guided exploration, where you prioritize getting to states with more uncertainty. This intuitively makes a lot of sense, but it puts a lot of burden on the process of trying to infer your uncertainty, which can be a pretty complicated problem, but something with a lot of research in it. And you can use something like intrinsic motivation, where you treat information as its own reward and then apply RL as you otherwise would, pretending that what you find rewarding is getting new information rather than just finding the thing that's extrinsically rewarding, the thing the environment defines as rewarding. I think this one is quite intuitive for scientists because learning stuff is quite enjoyable. It's quite popular. I think that is kind of the big reason. OK. So I'm going to talk about one more kind of model-free way of learning a value function. So this is basically to illustrate the concept of on-policy control as opposed to off-policy. So the way SARSA learns a policy is something really similar to Q-learning, but again, we're going to make a simple substitution. So what Q-learning does is this line at the bottom, where you're updating your Q function based on the value you were expecting and the reward you saw, and then the best possible value you could have gotten to next. So that's this max Q over actions. It says, like, if I had taken the best action, what would have happened? I'm assuming I'm rational. Maybe I didn't take the best action next time, but in principle I could have, so that's the policy that I want to learn about. SARSA does something a little bit more arguably realistic. It makes different assumptions about the agent. SARSA uses the action that you actually took, assuming that you're taking some kind of optimal policy. So instead of using the maximum Q, you use the Q of the state and action that you actually saw next. This leads to a really different profile in your behavior. And this is kind of an exercise for the group. This is an example called the cliff example. Not sure if that's its official name, but I think that's what people call it. And in this environment, you have this cliff, which is a block of states at the bottom that's associated with really, really negative reward. This is to a model of the kind of environment where you're walking around and there's some cliff, and if you fall off of it, you get a really bad thing that happens to you. Maybe you break a leg, maybe your days of being an RL agent are behind you. So these two strategies end up taking really different paths. One is using the best possible scenario to reason about which actions to take, and one is using actions that were actually taken and what the outcome was. Does anybody want to venture a guess about which path is being taken by which agent? Good. And do you want to provide an intuition as to why?
I think that the max will choose if the gradient from the negative rewards spread in the cliff.
Yeah, so that is exactly right. And the hand gesture you made up was also quite perfect. I'm not sure if that was deliberate or not, but the Q-learning agent is reasoning about the best possible action. The best possible action is not off of a cliff. So it's just not going to incorporate that into its value function. It's going to either go up or eventually to the right, because that's the best possible action. At first it's up, and then later it's to the right, and then later it'll be down. But the SARSA agent is learning about what actually happened, and it has a little bit of randomness in its policy, which means that sometimes it falls off a cliff. It really hated when that happened, and it's going to take the safer path from then on. And the likelihood of this happening and the badness of falling up a cliff will depend exactly what berth SARSA takes away from the cliff. So Q-learning is going to show up a lot in the rest of the tutorial. SARSA will make an appearance, but won't be featuring too much in the deep learning part. However, this notion of on policy or off policy, reasoning about the best possible situation or reasoning about what actually happened, reasoning from your experience, that is like a really fundamental way to divide up RL algorithms, and is really like crucial to thinking about what RL algorithm might be right for you. So I think one thing that I felt when I learned RL stuff, and one thing that a lot of people report, is that you're just learning like a lot of different words, and it's kind of hard to keep them all straight. So I just wanted to show this cheat sheet before we move on. Rescorla Wagner said, let's keep track of reward expectations. TD learning added over time. Q learning added control. And SARSA versus Q learning is the distinction between on and off policy. OK. Good job, folks. We're on to model-based RL. Hope you're excited. I like this part. OK, so what we just described, I didn't use this term, but it's called model-free RL. And that term is kind of meaningless until you contrast it to model-based RL. So that's what we're going to introduce now. And this gets to that fourth term in the agent definition, the one that is a model of your environment and how states relate to each other and when they're likely to give you reward. If you have such a model of the environment, you can use it to reason about what you're going to do. So model-based RL basically involves representing the underlying structure of your environment and when you're going to get reward, and using this model to support some kind of planning or reasoning process, or otherwise inform action selection. The model can be hard-coded. I could just give you a model. I could, I don't know, tell you something about biology, or you could learn it from trial and error. Maybe you learn about biology that it really hurts to touch a stove. It's kind of distantly biology. And then you just kind of have a model that's always the outcome. So a kind of simple example here is if you were reasoning about tic-tac-toe. This is very tractable to do with model-based RL. The rollouts don't go too far. The game size is pretty small. And a rollout is something where you basically sample actions, predict the outcomes, and then sample another action. And you can keep doing this until you get to some state that you know the value of, or you predict whether or not you win or lose the game. Oops. So contrasting model-free and model-based, they really have different pros and cons. So model-based learning is very flexible. You have a sophisticated model of the world. You can reason about different ways things might go. You can reason out of your experience. You can say, what if I had taken this action instead? And your model might have information about that. It's also very slow to update if something changes about your world. If I learn that I was wrong, I actually can't transition from here to there, I have to go around because something's under construction today, then I can just quickly update my model and then redo my reasoning and get new estimates. Whereas if I've learned the statistical reward expectations about every state and then something changes, I have a lot of relearning to do. On the other hand, computing with a model is really difficult to do. So if I have a huge model of how to play chess, I might have really, really long rollouts before I get to the end of a game. And people don't play chess by taking a rollout all the way to the end of a game. They kind of use some combination of heuristics and rolling things out for these local little tactical battles and skirmishes rather than rolling out to the end, because that's just not tractable with our working memory. The other thing is that model-based reasoning can be susceptible to accumulations of errors. You have a lot of different choices you make when you're reasoning through your model. And if you're wrong about something in your model, that can accumulate on every time you take a new step in your modeled environment. The model-free is more statistical, and it's anchored more tightly to experience. So these kind of error accumulations don't happen to quite the same degree. So to kind of illustrate this, I have this example of a really simple T-maze. And in this environment, we're going to pretend that there is a Fruit Loop in the top left corner. And when we get it, we experience reward because Fruit Loops are delicious. So what a model-free agent would do is explore this environment and start learning about which states ultimately lead to reward and update them whenever it sees reward happen surprisingly on a step. Eventually, reward diffuses slowly but surely down to the central state, and then at that state you can say, okay, the action to my right is rewarding, the one to my left isn't. Sorry, got that backwards. I'm going to take the one to the left. If I have a model and I modify something about my environment, let's say, whoops, oh, sorry, my animations are being a little sluggish. If I say, actually, there is a shortcut, and if I go to the right, I can skip right to the end, then maybe I now want to go to the right. Or maybe I move my reward to the right, and I want to now update my policy. The value of all these states will stay the same, but my model can change with just a single bit of information, which makes us more flexible to reason with. And this is more sort of a goal-based process. Rather than having stored the value of each action in the past and making your action selections based on that, you're going to say, what's the state of my environment right now? What are my current goals? And reason in that way. In this paper from Holland and colleagues, they show that you can really separate goal-based or model-based and model-free behavior. And what they did here is they basically just devalued a goal. So they trained an animal that if it presses a lever, it gets some food. But then later, it made it not want the food anymore. And the way it did that was pairing it with a lithium chloride injection, which made the animal feel ill. So now it does not prefer that type of food anymore. Anyone who's ever eaten something and then gotten food poisoning can relate to this poor little rodent. And then they test whether or not the animal will work for food. And in the case of moderate training, where the animal understands the experiment has done it before, they will stop working for food once they don't want the food anymore. But in the case where they've been extensively trained, they'll keep working for it. And the kind of theory for this is that early on, when they're newer to an environment, they're relying on a model of the environment that they're using to select their actions and decide if they actually, like what the outcome will be and if that's actually desirable to them. Whereas once they've been in an environment for a really long time, these choices have solidified into value estimates that take a long time to learn, but are ultimately support very rapid decision making. So then they rely on that system, and they're not sensitive to changes in the environment structure anymore. A task, a kind of like now famous task that's been used to disambiguate contributions of model-free and model-based choice to behavior is this one called the two-step task that was originally proposed by Nathaniel Dahl, though the version I have here is from this paper from Kate Hartley's lab by Decker and colleagues. And I think I use this one, and I think everyone kind of uses this one because it's adorable. It has monsters associated with it, and it's really intuitive. And the reason it's adorable and intuitive is because this was a version that they adapted to children so that they could study the emergence of model-based reasoning in children. Super cool topic. The structure of the experiment is this. In your first stage, you have a choice, which is which spaceship to get on, the blue spaceship or the green spaceship. The blue spaceship will take you to a planet where you will meet two monsters, and these monsters will give you gems. In one case, the monsters give you gems that have different values that are associated with them. So basically, you can get on a spaceship, you get to a monster, the monster gives you a gem, and the value of that gem is equal to your reward. So kind of a complicated experiment, but like children can apparently do it. And the key structure here is that which spaceship you get on determines which planet you're likely to go to, but not which planet you'll definitely go to. It would not be a good model for air travel. If you take the blue spaceship, you probably go to the red alien planet, but maybe you go to the purple one. And vice versa, if you get in the green spaceship, you probably go to the purple alien planet, but maybe you go to the red one. And then what you can do is look at what happens after these unlikely transitions happen. So let's say I get in the blue spaceship, and the unlikely thing happens, and I end up talking to the purple monsters. I guess that's always unlikely in some sense, but especially unlikely in the context of this experiment. Let's say it's really, really rewarding. What do I do next? Do I repeat the same action that led to my getting lots of gems from these purple aliens, or do I take the action that is more likely to lead me there in the future? If I take the action that was just reinforced, that's the more model-free thing. And if I reason, what's the thing that will get me here with higher probability, that's the more model-based thing. So basically, like, do you use experience or do you use your underlying structure? And it turns out people use some combination. This varies along several conditions: how stressed people are, how tired people are, how old people are. But if you're interested kind of in like how to disambiguate these contributions to decision making, this is kind of the classic paradigm to do it with. I'll get more into deep learning in a bit, but I just wanted to mention the deep learning version of model-based RL while I'm on this topic. And one of the big examples of this was AlphaGo. This was done by some folks I work with. I unfortunately had no involvement with it, although it is pretty cool. And basically what you do is you do this sort of tree search thing that I described with tic-tac-toe, except now you're doing it in the game of chess. Go, obviously. And what you're using to pick how you're going to explore down this tree is a neural network. And you have two neural networks that you're using for determining your behavior. Your policy network, which is going to say, what action am I likely to pick? And a value network that's used to estimate the value of the states that are happening in the future that you haven't seen yet, but might. It's kind of storing the expected value in a more model-free way. And you can basically search down this tree using this policy and see how valuable your estimated states are that you encounter, and use this to make predictions about how good different actions are. So you're basically kind of substituting the parts of model-based RL with neural networks, which is kind of the theme for most of deep RL. You just take some RL outer shell and stick a neural network inside of it. Often this makes it a lot less stable and a lot harder to get working. It has its own problems associated with that. We'll get into it in a bit. So this is one method for kind of combining model-based and model-free. The sort of key thing that's different about this compared to what other deep RL methods were using at the time was the model-based part, but it still has this value network that it's using, which is more model-free. And there's a lot of different ways that we can think about combining these up. This is also a really big neuroscience question, partly because it seems like there are different kinds of reasoning processes happening in human and animal brains that are emerging and dominant over different timescales, and also just like varying across individuals, how they're manifesting. But then also, I think more broadly, just because this problem of how different systems that have different information they're reasoning about and different relationships to behavior are really hard to think about, and a really big problem for trying to make more cohesive integrative theories in neuroscience. So a couple of these different options, I won't go into them in too much depth. One is that you just have both of them going at the same time, and they're both proposing actions, and you use some sort of arbitration to pick which one's best, and then use that action. That's the top left, model-free versus model-based competition. You can also have a model where model-based is feeding model-free. You learn a model of the environment, but the only thing you're doing with it is sampling different trajectories from that model so that you can train up your value function and have a better model-free system. You can also have it where model-free is serving model-based, and you're doing this sort of tree search to some depth, and then whenever you're tired of tree searching, or you think you've searched far enough, or you've just run out of time, you use whatever value is stored at the state that you got to. And then finally, there's other ways to combine it, like using things like cumulants or successor features, which sort of learn statistics about the transition structure in the same way that you can learn statistics about reward. So what model-free learning is doing is learning how much reward do I expect to get under these different options. And you could say, how many states do I expect to visit with some quality under these different options? And that kind of gives you some flexibility to reason about different outcomes, but also compresses a lot of things into statistics. You can't do this sort of action outcome-based reasoning where you sample an entire trajectory, because you've kind of smushed your predictions into a single estimate. And then I think I'm going to try and skip through this section a little faster, because I think I was a little self-indulgent and maybe made it a bit too long. But I'll talk a little bit about hippocampal contributions to model-based behavior. There's some work showing that hippocampus contributes crucial things to model-based behavior. If you look at how animals with hippocampal inactivations perform in an animal variant of the two-step task, you see that their planning performance is impaired. And then you can see the same thing in human subjects that have hippocampal amnesia. The animal paper was done by Kevin Miller and colleagues, but actually there's a follow-up at Cosyne on Friday if you guys want to check it out. And there's a bunch of different theories about exactly what hippocampus might be contributing to model-based behavior. But one thing that's particularly evocative in the view of the kind of model we have of how model-based reasoning might happen, these rollouts, is that you have a lot of sequences in hippocampus that look like they could be doing something kind of like rollouts or samples from a model. So as an animal is running along, you get these sequences that sweep out in front of the animal called theta sweeps. It's kind of like if you were moving up a piano by playing 4 keys at a time. They just kind of continuously sweep in front of the animal a little bit ahead of it as it's running along. And then offline, when the animal is not behaving, you see these sharp wave ripples, which is this unusual activity recorded in the local field potentials that tends to be associated with sequences. So this might be when the animal is asleep, they're very common then, or it might be when the animal has just finished a trial and is sitting there grooming or eating its reward, and maybe thinking about what it just did, maybe thinking about nothing at all. So there's a couple different properties that these sequences have that's also especially evocative in the view of model-based learning. One is that the activity cycles before a decision, as if sort of considering the 2 different alternatives. As an animal starts to reach a decision point, you see this sub-second cycling where the place cells population in hippocampus will decode to either the left or right choice. You can also see these sequences that go to locations the animal hasn't been to yet. So this picture is my own. That's not from the author's paper, but it does kind of capture the structure of the experiment where a rat runs to the end of a T-maze that's blocked by a glass wall, and it can look over the wall and see what it can do next, but it can't do it yet. And the authors record sequences that go down the trajectory that the animal is about to go down. Basically, the same cells that fire when it's looking are the ones that later fire when it's doing it. And then one that's a bit more subtle, but I think also really interesting, is this paper from Stella and colleagues that showed that the statistics of hippocampal replay when the animal is asleep are different from the statistics of hippocampal activity when the animal is awake. And this basically means that it looks more like you're sampling from a model than just sampling experience directly. Because if you were sampling experience, you'd get more similar statistics. So a paper that I guess is not such a recent paper now, but is from 2018 from Matar and Daw, really crystallized this in the view of how these sort of sequences might relate to reinforcement learning. And they basically hypothesized and showed that you could explain a lot of sequences in hippocampus with this idea that the sequences that are being played are those that are optimal for updating some value function. So this is the idea that your model is serving your model-free process by sampling different states that allow you to accurately have a value function that reflects the real value of your environment. And they broke this down in more detail, but it's a great paper. You should check it out. Okay, I'm going to skip that for now. Okay, so that's what I've got on model-based RL today. And now I'm going to move on to function approximation and deep RL. And I should say this is like a really good time for questions, partly because the material is about to change a little bit, and partly because I'm a little nervous nobody has asked a question yet, because there's like no possibility I'm being 100% clear about all this. And it's a tutorial that should be some amount interactive. So I want people to feel free to ask questions if they have them. Yes? So the question was, I talked about how reward works in the model-free context, but how does it work in the model-based context? Or like how does the animal reason about it? Yeah, so I focused mostly on the problem of representing a transition model, and because that's kind of the part that's the most complex to learn about. But for model-based reinforcement learning to work, you also have to represent the reward function. So you represent basically how you can transition across your environment and which states give you reward / how much reward you get at those states. So when you perform a rollout or some sort of sample through your model, as you do that, you compute, am I getting reward at any of these states using your model of the reward function? What's that? I'm not sure why it wouldn't. I think basically, most of the dopamine stuff has either been, that I'm familiar with, I'm not really sure how the reward prediction error hypothesis maps onto like simulated rewards during a rollout. But I think that's often more often contextualized in the context of model-free reward prediction error learning that's used for a value function. But I think the reward that basically like you should have an easier time learning an instantaneous reward function than you'd have learning a value function, because you don't need to propagate it over your environment. You just need to learn it at a single value. I think dorsal medial striatum tends to be more associated with like learning of a goal that could change under different sorts of situations, like is more involved in cases where you have something that's devalued, whereas dorsolateral seems more like model-free. Yeah.
It seems like there's a lot of different ways to have and use a model. Do you have a sense for which among them in practice seems to work the best?
There are so many ways to have and use a model, and it depends a ton on the problem. So there's a really lovely paper by Jess Hamrick which is titled "On the Role of Model-Based Reinforcement Learning," and they look into this in a couple cases. And they find interestingly that in a lot of environments, the part of learning a model that's important is like your representation of your state rather than actually using the transition function. That's like a pretty specific deep RL thing. I mean, it really depends. I mean, I think basically like some of the things that trade off with each other is like how big is your environment? How fast are things changing? Does everything change, or are only a few different things changing and you really only need to be flexible about like what you're going to do at a decision point? I don't need to represent the possibility of turning around at every point as I go down a hallway. Once I get into the hallway, I'm probably going to come out of the hallway, and I really only need to represent choices at a higher level of abstraction. I think it really, like, the thing that's hard about it is it depends a lot on the statistics of your problem, and it's hard to characterize problems in the real world. Yeah?
Do you absolutely need a reward? I mean, because you were mentioning how to model, for example, theta-based precision or spike activity over in a track, when at the end of the track we are going to get a reward. But it does happen also when it's free exploration. How do you predict, how do you model the firing activity without a final reward?
Yeah, that's a really good question. So basically it's like, do you need reward to explain this, or can you, because these are all things that just happen as the animal's running around and have nothing to do, and you know, do they happen when reward is not happening? And the answer is yeah, these happen just as the animal is exploring the environment, and it's really more of a hypothesis that these are serving some downstream function, or maybe more accurately, like it's sort of a normative framework of why you would bother learning the statistics of the environment, how that might ultimately relate to your behavior. The Matar and Daw paper about like replaying things, that actually does depend on reward because they have some specific predictions about why you might have replay when you get to rewards and how that would fit into a normative view. But a lot of this could just be like you learn the statistical structure of your environment in more of an unsupervised way, and maybe you use it for reward problems, or maybe it's just kind of part of being an animal or something and isn't immediately useful. Yeah?
Because, for example, in another paradigm where you are studying spiking activity during sensory perception, any kind, can you predict the spiking activity, for example, regular tones versus deviant tones? You can't predict more or less, you can encode the spiking activity from there. There's no, I mean, you can put a reward at the end and give more value to this spiking activity, give it to a specific sound, but you can also get a different pattern that it's easy to decode without a reward. So are you able, can we use this technology to predict this firing activity?
So I think, let me see. So basically, I think you're saying like if you have like different kinds of codes in response to different sensory cues, is this kind of a similar question? Like if they're just different and you're seeing different codes and it doesn't necessarily, like the difference is purely sensory, it doesn't need reward to be driven?
For example, in a football paradigm,
Yeah.
there's a predictive value, right? Like
Yeah.
beep, 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 beep. So the beep, and you weren't expecting it. So you have these kind of expectation values, but you don't have a reward at the end. How this affect your algorithm?
Yeah, so basically for, it's a cool question. So basically for model-based learning, you would still learn something because you're trying to learn some structure of the environment. It's really using unsupervised learning as a sort of sub-process of RL. So you would learn something about your environment, which is that you sometimes get these surprising things that happen. And models of dopaminergic contributions to model-based learning would predict that you see some firing associated with this. So like Jeff Schoenbaum has like some really nice work on this, and Angela Langdon and Sam Gershman. And they say like they're state prediction errors rather than reward prediction errors. You should still get stuff. And I think like the thing that comes back to is just the idea that like even if you want to adopt this normative perspective where all of the things that you're learning are ultimately supposed to relate to behavior in some way, and like behavior that leads to more reward and ultimately more Darwinian fitness, then you still might want to learn structure of the world that's not immediately useful. Because let's say I was just doing model-free learning, and this surprising thing happened, and none of it had reward associated with it, and I just learned nothing at all. That also seems obviously wrong, because there might be some reason why these things are different, and that reason might be predictive of something that I care about optimizing later on. So I think there's kind of these two views I could say. One is that you just don't need RL to explain it at all, and another is, or I guess it's not about using RL to explain it, I guess, but it's like maybe RL is part of the story there, in that you could think about why the sort of unstructured representation that happens here might support or not support a later reasoning process. Or you could just say, this is a statistical problem, I'm narrowing my scope, maybe some RL process outside of this uses it, maybe it doesn't, but that's also a perfectly valid way to do a research question. Yeah, we'll do one more and then go on, because I'm actually not totally sure how much time I have left.
So I would like to go over the transitions between model-based and model-free RL across learning. There is any model-free RL in the brain? I mean, what is the difference between having an unsupervised learning process in an environment and then consolidating the model of the world and then using that model of the world when you already have some notion of how the world works?
Yeah, so I guess, is there any model-free learning happening in the brain? I guess it sort of depends on where you look, I guess. So I would say the reward prediction error hypothesis is that whole algorithm that it's using is model-free. And a lot of the sort of more complexified, rich versions of it are also model-free and are basically saying you're linking your incoming observations and the actions you can take to a value function or to some kind of policy that you're directly manipulating with the statistics of reward, rather than learning a more explicit model. But I guess if you have if you assume you have both processes happening at the same time and they're both affecting other parts of the brain, you could start getting abstractions that really serve either, that basically you could start. You have a sensory model of your environment that's taking into account structured aspects that might not have anything to do with reward, and those are feeding into your RL process. So the extent to which your state representation is capturing information about the structure of the world that itself kind of incorporates some of the information a model might usually have starts to make the lines a little bit fuzzy. Does that answer your question, or did I kind of take it too abstractly? Okay.
Just a little bit. It's just I found counterintuitive when you explain the paper that says that at the beginning animals rely more on model-based RL, and then they go to model-free RL.
Yeah.
That's a little bit weird, because I guess that you need some experience to consolidate a model of the world, right?
Yeah, so that's also a really good question. I think probably because learning a model itself takes time. So at first they just aren't really they aren't doing anything. They don't really understand the structure of the environment yet. Presumably they're learning both a model and a value function. It also could be that these are adult animals who have spent their lives learning stuff, and they might be bringing some prior information to acquiring their model that applies more to the model case than the model-free setting. But yeah, it's a good question. Is it a quick question? Yeah, go for it. All right. Thank you for your honesty.
So when you wrote the update rule for the Q learning, there's a maximum over all the actions that's taken.
Yes.
Is that something that requires foreknowledge of the whole action space and the results of all the actions? Because
Yeah, sure. So basically he asked, in order to take the maximum over actions, which is a thing you have to do for Q learning, do you need to be able to keep track of the value of all possible actions? And the answer is yes. You don't necessarily need a model of your environment to do this. You just kind of the way that it will be represented in the coding tutorial later, which kind of gives away an answer, but don't, you'll forget, is you have a bunch of states in your environment and a bunch of actions you can take at each state. And this is a table, and you keep track of the values of different actions every state. And so, yeah, you just need to have some sort of explicit representation of all the different actions. This is kind of hard to do in environments where you have continuous control, like if you're balancing a stick, that's the cart pull problem, or you're trying to control a robot body in continuous space. So other methods tend to be used besides Q-learning for continuous control. Yeah, good question. Okay. 35 minutes, awesome. Swimming in a sea of time. All right, so now we're going to start with the question of representation, something philosophers have argued about for a very long time. But we're going to consider it in the simplified setting of a traffic light. And so far, the way we've been representing our environment is as highly abstracted and tabular. So if I basically the representation I might use for this traffic light is that I'm going to map it onto a one-hot representation, where if the light is red, we put 1 in the first slot, and 0 everywhere else. If it's yellow, we put 1 in the second slot. If it's green, we put 1 in the third slot. So that basically means I have these categorically different states. I don't have a ton of them I need to think about, and I can learn the Q value for every action given these different states. So here I might have the Q value of braking given the state, of pressing the gas, of steering. I took the liberty of adding these values as 1 for braking and -1 for gas, but it really depends on one's risk-taking preferences. However, this is a very hand-engineered human choice, and B, it's a very, we had a lot of other options we could have picked, and it's a big space to choose from. And different representations might be better for different types of problems. So here we have the one-hot that we're using. We could also represent this as a kind of cartoon, which has more of the color information. And red in this context might relate to red in other contexts. You've seen it because you are keeping the color information around. You can't tell probably because this image is so small, but this is just a super pixelated version of the image above. I could just represent it as an image, but maybe a really downsampled one. I could ignore the traffic light altogether and just represent which intersection I'm at. Probably a really bad idea. I could add information to my representation, like the time and the location. For instance, you can't make a right turn on red in this country, and that's really good information to know. Maybe if it's 1 in the morning, I'm a little less conscientious about whether I stop for a red light. Who knows? Or I could represent it with natural language, something that is increasingly popular nowadays because we actually have the tools to do it pretty well. So here I wrote a very evocative sentence. She drove up to the traffic light. Her foot hovered lightly over the brake. The red light reflected off the dashboard, reminding her of the sunsets in her hometown. She then braked or steered or what? And some kinds of predictive language-based models could tell you. So there's some really lovely work from Yael Niv's lab. This is Wilson and Niv 2011. There's also some later articles that followed up on this. Angela Radulescu, who I thought I cited here but don't see here, wrote a really nice review paper on this. But this basically, they studied the problem of how humans learn to attend to relevant features. And found that rather than doing a fully optimal Bayesian inference based on what they'd seen before, they seem to make hypotheses that certain features are relevant and then test them with their selections. So maybe I see these shapes in frame A, and then I pick the square, and then I get a point. Which one do I choose next? This square has 3 features associated with it. It is green, it is a square, and it is kind of plaid checkeredish. So which of these features do I try to experiment about next? This is a big part, we think, of how we simplify the environment that we have to reason about. And I have a little picture of exactly what this would look like, again, in my favorite team is. For this problem, we're going to start to think about how we would reason, not over tabular values, where we know the value of exactly one state and one action, but over the value of different features, which might be present or not present to varying degrees in different things that we observe. So here our features are going to be some hand-picked ones, whether you're on arm 1 or on arm 2. We're going to map all of our states into this space. And then let's say I find a fruit loop on arm 1. What do I do with this information? Ordinarily, I would have just incremented the value of the state where I got the fruit loop And then later, I would have visited the state right before that and incremented its value, so on and so forth. But here, because we're representing this as a feature, I'm going to update the value of that feature, which applies to varying extents to the entire arm. So now all of these states get a little bit of the blur in value. And this is very good for this kind of representation. This is a very efficient sharing of credit across all of the states that are all kind of nearby this reward. However, if actually the state right next to the Fruit Loop was associated with a really bad reward, this would be kind of a problematic generalization because I'm now kind of grouping everything together. So your representation really needs to respect what's similar and what's different about how the states in your environment relate to reward. So a while back, some people had this nice idea. We should just learn the representation with a neural network, and then we won't have to make all these hard decisions. There's a bunch of different versions of this, and this wasn't the first one, but it was the first one to make it work for Atari games, was this idea of using deep Q learning. So here, instead of learning the Q value of a state and action, we're going to learn the Q value of an observation and action. So our observation is going to be a very high-dimensional input, an image, maybe a frame of some Atari game, maybe the last several frames that you've seen. And we're going to pass this through a neural network, and we want the output of that neural network to be the Q value for every possible function given that input observation. So here we're going to predict, instead of like having a table where we have states and actions, we're going to have a function that outputs what would have been a row of that table, a row of Q values for every possible action. And then what we're going to do is we're going to use a really similar strategy of temporal difference learning to update the neural network weights in order to minimize the difference between the predicted Q value and then what was actually observed. And what was actually, and what you're going to use as the actually observed is the reward that you see, and then the maximum Q value of the actions you can take that are available to you, which is just given by your output. So you make some predictions, you see how it goes, you try to make that prediction small. It's really the same logic, except for instead of changing your values in a table based on your surprise, you're going to update the parameters of your neural network to make this difference small. And this ends up working well for lots of games. They showed the kind of original paper that sort of like made DeepMind a thing was showing that this could solve a lot of Atari games quite well and even beat people on quite a few of them. So hooray for us. There's also been a decent amount of work now using deep RL to model the brain and different neural processes. And I think this one is a really straightforward demonstration of it. Here what the authors did is they looked at several different deep Q networks that had been trained to play different Atari games and compared their activations to the activity in the brains of humans that were playing the same Atari games. And they found that the hidden layers of the DQN to varying degrees exhibited resemblance to the voxel activity in different parts of the brain. And they could kind of say, to what extent are these different areas explained by different stages of processing in a neural network? So now I'm going to introduce something called the deadly triad, which tells you two things. One, that this is going to have some problems, and two, that RL researchers can be a little bit melodramatic. And the deadly triad is this combination of off-policy learning, and Q learning, remember, is off policy because we're using the maximum action, not the actual action. Bootstrapping, which is a term that hasn't come up yet, but is intrinsic to all the processes that we described, where we're using the value function on the next step to update our estimate of the value function on this step. We're basically letting part of our training signal be something that's produced by the model itself. And then this thing, function approximation. And function approximation is what I showed, where you have this feature where many different observations share features. So if I learn something about one state, I might learn things about other states as well, based on the extent to which they share continuous features. And when you combine all of these things together, you can get divergences because the model is using a lot of speculation to train itself. So basically what function approximation allows you to do is learn something about other states that aren't present right now. States that share features with your current observation but are different and were experienced differently from your current observation. And if you then bootstrap off those values, if you say, well, this observation has some features of that one, and I'm going to use it to train the other states nearby that had, based on the prediction error of what I thought I was going to get and what I actually got here, you start taking some kind of like spurious information and moving it really far around your value map of the environment. And this can lead to like pretty severe instabilities. In principle. In practice, sometimes it's fine. Also, there's a lot of tricks that people have come up with to make this work. So one of them is experience replay. And experience replay solves a couple problems. One is this issue of kind of mixing up your experience so that you're like learning about many states at the same time, which can be stabilizing. But the main one it kind of focuses on is this fact that your experience in the real world is really likely to be highly correlated. Reinforcement learning describes how an agent is learning online. It's moving through the actual world and trying to continuously update its estimates about what's good. But the problem with the real world is, there's many, but one of them is that your experiences are very likely to be correlated over time. If you look at these different trajectories, you're never going to move from like that corner to that corner without a ton of time happening in between. They're just too far away from each other. And if you look at your experiences, they're going to reflect this correlation structure. And if you use these experiences to learn, your policy is going to become very temporarily biased to your current experience. I'm in the pink stages, I'm only going to really care about learning pink stuff. And the fact that this model also needs to apply to the blue regions is just not going to be reflected in my learning rule. So what a replay buffer does is it stores a bunch of these experiences and replays them randomly to sort of simulate interleaved experience. So if this was the actual order of your experience, then you start mixing in experiences that you remember from far away so that you're learning about the new environment while also maintaining your performance on old states that you've seen before. And this is really useful to keeping a stable algorithm. So if you're, like basically the issue that can happen as it relates to the deadly triad is if I'm only prioritizing my policy over in that region of the space, but that region of the space shares some features with there, then I've just updated my policy a lot about features that apply over there without having actually seen any features over there in a really long time. So I'm overgeneralizing what I've seen over here to something that's far away, unless I kind of intersperse these experiences together. So there is this kind of, yeah?
Is this related to like the DynaQ algorithm mentioned earlier? Like, are these two like the same, or is there a difference?
So the key difference there, it's similar in that you're replaying from a model, and it's so like, I guess, sorry, it's similar that you're replaying experience that isn't happening right now. The key difference is that with an experience buffer, it's something you've experienced, where with Dyna, it's a model you've learned of the environment and you're sampling from that model. So it's not quite the same as an experience buffer as it's implemented in like these reinforcement learning algorithms, where you're literally taking the observation in raw pixel space that you experienced, storing it, the actions you took, the reward you got, the state you saw after that, and then re-implanting them as if they're experiences that you're seeing now. As it relates to the brain, they might kind of reduce to something similar, because of course, like any model we have of a replay buffer in the brain is not exact. It has to be approximate because there isn't really, it's physically ill-posed to just take the entire world as it is now and have that exactly and be able to revisit it. So you really would need to make some sort of memory system which might end up just amounting to something like a model in the end. Yeah, so this question about how the brain prioritizes experience, we can think about it in the context of a replay buffer. We could also think about it in the context of like how do you pick which samples from a model to sample to train up an RL system. There's a couple different ways that you can that people like to sample from these models. The original DQN paper, and I think still the most popular thing, is just keep track of your N most recent experiences and sample from those. You can also use reservoir sampling, which is basically just uniformly sampling across all of your experiences you've ever seen. This might, if you keep really old experiences around for too long, this might bias your policy in ways you don't love. Like this might be why babies don't really learn anything till they're 2, but that's vaguely, sorry, they learn things, but they don't like they have infantile amnesia and they don't record like episodes in quite the same way. Maybe we don't really want to be biased by those really, really early experiences. Oh, thank you, yeah.
So I'm guessing that like you can't really, like when you're training these algorithms, you can't really look forward in time, right? You can only look back at the past history. So is there, like it isn't immediately obvious to me like how far back do you need to look, you know? Because there might be some really, really long time scale correlations in the behavior.
Yeah. Yeah, so basically picking, oh, sure, thank you. So basically the question is how do you figure out how far your replay buffer needs to look? And this is also a bit of nuance because there's trade-offs in both directions. If you look too far in the past, then your replay buffer will contain a lot of experiences from a very outdated policy. It'll maybe include a lot of states that are so suboptimal you don't even really go to them anymore. Or maybe, like in chess, for instance, there's openings that people just don't even use anymore because they were already proven to be wrong. People have trouble reasoning about them sometimes because they're so unlikely. On the other hand, if you don't go back far enough, you aren't really successfully decorrelating your experience. So there isn't really like one single answer, so much as like how would you balance these two trade-off elements. And the trade-off elements being like you want the most recent version of your policy, but the most representative spread of your environment. There are some models, like some things that start to address that are things that use learned policies for recalling things from memory or incorporating things. So there's a notion of neural episodic control. It's not quite the same because you're not replaying things, you're rather just like reinstating them to your current policy, but it does have like a learned nature of like looking into your replay buffer and trying to figure out what's the most relevant thing to look at. The Matar and Daw paper also has an angle on this, although it's for the tabular case, not the deep RL case, where you could say, you have a notion of like what are the optimal things to replay. Let's say we're replaying those. That explains things. But it computes them by saying like, by looking over all the possible replay activities and saying which one of these would have been the most optimal, does that look like what the brain did, rather than, you know, which is kind of a hard way to do it in practice. Presumably there's some heuristics that the brain uses that says these are a good thing to replay based on relevance and, yeah, based on relevance. Yes?
The problem was that you had a correlated long sequence. Is it equivalent if you had something like a calcium display or some way to decorrelate that you know that to change the learning rule and not the replay? You always learn, but acknowledge that you're learning correlated stuff and to correct while you're learning.
Yeah, so the question was basically like, is replay, let me know if this paraphrase still captures the essence. Are there ways that you don't need to use experience replay, but you decorrelate your consecutive samples in other ways? There are techniques for doing this. The reason replay is so commonly used is because it is kind of like simple and external to the model. You still let it learn its own features. You're not saying you have to decorrelate these things or adding anything mathematically sophisticated to do that. You're just kind of saying like, store your experiences and now you can scramble them up and use them. But there is stuff about like either feature engineering or pre-processing or methods that might also decorrelate your consecutive samples in a more principled way. Yes, and then this will be the last question until the break because I might run out of time.
In the Shull paper, were they concerned with the most surprising experiences with respect to the state of the model at the time? Like, did they store the surprise at the time, or are they looking at the most surprising experiences with
They use the, I'm like 90% sure they use the surprise at the time. Although now that you ask, I realize I'm not I might have just assumed that. But I'm pretty sure they use the surprise at the time rather than like, yeah, they must actually, because they're making the decision when to store it. Basically like based on the current, sorry, the question was, in the shawl paper, did they use surprise at the time when it was experienced or later on? Because maybe later on, you've already learned enough about your environment that what you saw isn't surprising anymore. And they use surprise at the time. So surprising events are more likely to be put in your buffer and then resampled later. Presumably, these things will be replaced later on because your buffer fills up. So they only keep getting in there again and again if you remain surprised. OK, cool. So just to say quickly, and then I think, yeah, I've got, what, 15 minutes? Cool. So this relates to some pretty deep problems in neuroscience about how memory systems might cooperate with each other. You can draw a pretty nice analogy between this idea of an experience buffer representing specific experiences and a value function representing something more consolidated and precompiled and ready for rapid use. Not the only way you can put up a complementary learning systems problem. Sometimes there's a lot of ways to do it. But it is one thing that kind of captures some aspects of this problem. So this question of like how exactly experience is turned into knowledge is, of course, a really, really deep one in neuroscience that captures a lot of interesting questions. And this is sort of the RL version of it, I would say, or even maybe the model-free RL version. There's one more trick that's super useful to getting deep Q networks to work. And this is the notion of a target network. So this harkens back to the deadly triad, where you're bootstrapping by using your current value function, both to make a prediction and as part of your term that determines the actual value. Your actual value is the reward you experienced right now, and your estimated value after that. And of course, actual is maybe not the best name for something that you're estimating with a function that you're learning online. And because you're bootstrapping something that is susceptible to continuous changes from faraway parts of your environment, using this can lead to problems. So one thing people do is, again, a pretty simple trick where they just take the current Q network and they make a copy of it. They take all of its weights, they take an identical version of it, and they put it over here, and they call it the target network. Then, as the agent continues navigating the environment and learning about stuff, the model that it's updating is the prediction network. And the model that it's using for its target prediction, for computing the actual value, is this one that's a copy. So this copy is basically updated more slowly. And having a copy of something, a target that's updated and changing more slowly than the prediction network, lends a little bit of stability to your process. It basically means if you see something on one step and make a change, that isn't immediately going to propagate through to the rest of your environment, leaving a value problem you have to chase down later. It has to happen for a while before you start solidifying something into a target network that you're going to copy over more slowly. You could get unlucky and copy your target network over right after something kind of spurious happens, but at least it's a little bit slower and more stable. OK, and then the next thing I want to talk about is policy gradients. And this one I feel like I've betrayed you slightly, because everything I've talked about so far has been about learning expected reward and anchoring your behavior for this. But you can actually pull back that curtain and just say, why don't we reinforce the behavior directly? And the reason I have a picture of a bunch of tiny economists in the top right corner is because value is arguably a concept made up by economists, where you have the expected utility of different options you can take so that you can make comparisons in a common utility language between choices. And this idea that we have to compute value explicitly, how much reward we're going to get, and then work backwards from value to our behavior, isn't the only way to do things. We could just take a bunch of actions, see which ones went well, and then make the actions that went well more likely and the actions that didn't less likely. And this is exactly what policy gradients does. So you start with some random initial policy for acting in the world. You sample some actions with your environment. And in proportion to the observed return, you adjust the weights of your policy predicting model in order to make the actions that went well more likely. So basically, you're just only using reward from actual experience trajectories and then modifying the parameters of a policy. You don't actually have an explicit thing that's computing how much expected reward you're going to get. So this is an on-policy algorithm. You're using actual trajectories you've taken and the actual rewards you've seen in order to modify the policy that you're taking. The main issue with it is that policy gradients can have high variance. And this is because some trajectories you get rewards, sometimes you don't. Reward can be very variable, making the gradients very variable. And in case you're interested in using it, two of the most popular variants, I would say, are PPO and A2C. PPO is just a policy gradients method, and A2C is called advantage actor critic. The two is because two of the words start with A. There's also now a version A3C for training something like A2C on multiple different threads. And both of these methods, what they do is they have like a lot of different tricks inside of them to make the policy gradient estimation process a bit more stable. And at this point, I think it's probably good to refer explicitly to this feature of RL and maybe all of machine learning, which is the model zoo, which is that there's lots of different types of algorithms. Even in the early days of RL, there's like Rescorla-Wagner and TD and SARSA and Q-learning and all these different things to think about. And now all of these different lineages have their own deep versions without even getting into model-based RL, which has like infinite different combinatoric options. You have all of these different types of models that you can use. And if you want to get into deep RL yourself, you might be like, all right, Pavlov is fine, but like I really just want to know which deep neural network I'm supposed to use to train something on this problem that I happen to have. And the fact is, like, all of these different models have different pros and cons associated with them. Two of the major considerations are whether your action space is discrete or continuous. And another big thing that will divide up your model space is if you have one GPU or lots of GPUs. That's kind of single or multi. Or if you don't have any GPUs at all, that is a thing that happens. So continuous or discrete is a big question. How long can I afford to train, and how good does final performance need to be? Something like DQN is thought to get very good final performance and be efficient in its use of experience because it uses this replay buffer, but it's not efficient in its use of time. It takes a long time to converge. Something like PPO is often really popular because it seems to converge faster and be kind of stable. Lots of people really like to use PPO. PPO can also be used for discrete and continuous problems, which is kind of fun if you want to use the same model for two things. The other issue is just the stability of the problem that you're considering. Different RL algorithms have different stability profiles. So if you have a very noisy environment with very, very rare reward, that could be an issue, and you're going to want to pick something that's more stable. And let's see. Oh, yes, and of course, because we are neuroscientists, and this is a neuroscience conference, the neural computation you're trying to model is also going to be a really big part of your design decision. If you're trying to, like, a lot of people have used actor-critic models when modeling the brain because the parts seem to map on nicely to basal ganglia. Although, of course, there's lots of papers, wondering about that and making different hypotheses there too. At high level, I kind of just said there's a lot of options and a lot of reasons to pick them differently, but I hope that these kind of different axes can help you start to make sense of the model zoo. All right, so I'm going to get into a couple of the challenges with deep RL, sort of to close. The last section of this is philosophical considerations, but I think that's also would be really nice to do during the tutorial, either at the beginning or end, so I'm happy if we don't get to that. So a big part of the challenge for RL is this credit assignment problem. You have very high dimensional inputs. You don't get reward very often. And the model is really only trained to represent things that are immediately useful to reward. This gets to the question of if you ignore the surprise in your odd one out paradigm, then you're ignoring a lot of good information about the world just because reward coincidentally didn't happen. So there's been a huge, huge amount of interest in combining these with unsupervised learning. This has been going on for a while. An old version, relatively old version of this from '93 is to use predictive representations. This is something I've personally gotten a lot of mileage out of and also has spawned a lot of different directions in the machine learning field. Basically, the essential idea is that a reinforcement learning is a problem about predicting upcoming reward. And you can separate this into a problem of predicting on average what will happen, a predictive representation of your environment, and also representing how much reward happens at each location. This is one of those kind of hybrids between model-free and model-based. So we had a paper a while back hypothesizing that this was one of the ways that hippocampus contributes to a model-based like style of reasoning. There's also some cool work showing that humans use strategies like this to learn and to generalize when things about their sequence statistics change. And then both this and also other predictive models have sort of found a future life as predictive auxiliary objectives for deep reinforcement learning. So the idea is here, you want to try and learn things that are not just reward. So you want to, and one idea to do this is just learn to predict what's going to happen next. And you can make this an objective for a neural network, just as you could make it a matrix that you're going to learn with expected summaries of what's going to happen next. So these are basically like ways that you can either train, as you're training a model on something with reinforcement learning, you can have another head that's trying to predict what's going to happen and forcing you to represent more of the structure in your environment. You could also say, before you even get to the reinforcement learning problem, I'm just going to try and learn to predict what happens next. And then whenever I do start getting rewards, at least I'll be ready because I'll have some sort of structure to bind it to. A more modern take on this is this idea about using decision transformers, which springs from this idea of control as probabilistic inference. And this is getting to that distinction I made earlier where you can have, this is treating a reinforcement learning problem with a non-reinforcement learning method. And basically what these methods do is they learn the predictive statistics of your environment. You sample lots of different trajectories through your environment, see where you were, learn a model of how you tend to transition and how much reward you got. Then what you do is you condition on getting a lot of reward and see which trajectory is the most likely. It's basically framing a control problem, picking which actions you're going to take, as an inference problem, inferring which actions were the most likely given that great things happened to you. So older methods, of course, use different methods for this, but the most exciting modern method for making predictions are transformers. And so you can set this up as a decision transformer problem, where you use a transformer to do your predictive learning, and then invert this to condition on a lot of reward and figure out which actions were the most likely. Another version of treating reinforcement learning as a sequence learning problem is to use meta-learning. So this is some modeling work from Jane Wang and colleagues, a colleague of mine, and kind of the canonical thing that this is trying to help with is this fact that as you are exposed to more learning problems, you don't just learn about a single environment you're shown, you also get better at learning problems in general. So in this task, the monkey has to pick whether it wants the green object or the orange object. At first, it takes it a while to learn the reward associations, but it starts getting faster and faster and faster as it's shown different pairs of objects with the same reward structure. Whoops. And if you treat reinforcement learning as not just a problem about picking your actions within one task, but as a problem where you're going to have many actions that you have to pick, and you want to maximize your reward starting as early as possible, then you can start learning over tasks rather than within a single task. You're kind of learning a way of finding good solutions. So like meta-learning, you're learning to learn. Okay, And then here are some fun things I didn't really have time for, but thought would be really exciting. Hierarchical RL, super cool. There you learn a high-level policy that says what should your goals be, and you learn a low-level policy that figures out how to execute them. Multitask RL, where you try and learn to share information from different related tasks. Auxiliary objectives, like predictive auxiliary objectives is just one kind. There's lots of different ones you could think about. Incorporating uncertainty is something we talked about with exploration, but also can be used to inform behavior. It's a big topic. And episodic RL, which is really like combining your experience buffer in a more clever way. I also wanted to, in my remaining 2 minutes, just talk about some applications of RL and where this is used in the real world. I think two of the exciting ones that some of my colleagues did are, one, using reinforcement learning to predict protein conformations based on the sequence of proteins that you get. Basically, there's very good simulators for evaluating the energy of a configuration, but it's very computationally challenging to figure out, to reason about all the possible different conformations and see how good their value is. So you can use reinforcement learning to search the space of protein conformations more efficiently. We've also used, we broadly construed, they've also used reinforcement learning for complex control problems, like controlling the cooling mechanism for a data center. A sort of more dubious one, and one that I'm not even really sure where it's being used because it's all proprietary, is using reinforcement learning as part of recommender systems or marketing or advertising systems that are basically trying to figure out what humans are going to engage with in some way. The reward signal is, did you click? And the algorithm is trying to optimize things to get you to click on them, to get you to watch them for longer. I think the somewhat scary goal of really just trying to maximize your engagement as much as possible, which is itself sort of a tenuous proxy for your actual preference. And then, of course, the most exciting one, in my opinion, is fine-tuning foundation models for human preferences or for really any other possible objective you might want to have. The explosion in AI recently has been unsupervised learning. And the reason for that is that a lot of the things that make reinforcement learning hard don't apply in the case of unsupervised learning. Reinforcement learning has to explore to get all of its data. That's really hard to do. Reinforcement learning only learns when there's a reward present. It ignores a lot of information about the environment. Unsupervised learning doesn't have to do that. So if you have tons and tons and tons of text about what humans are saying to each other, or tons and tons of images that humans have taken of the world or artists have produced, then you have a huge amount of signal that you can start learning the statistics of and the patterns of. And this is why ChatGPT is amazing and Stable Diffusion is amazing. And these models are just incredible because they have this massive data set that they can really distill and the algorithms to do it efficiently. Where RL starts to come in is when you want these models to not just do what's statistically likely under the data set, but something that's optimized for a particular task. For instance, if humans prefer not getting yelled at by a language model, maybe they're more likely to say, I found that interaction not rewarding, whereas this other one where it helped me find what I wanted was very rewarding. People have basically used these sort of human scores to do an additional reinforcement layer of fine-tuning on top of unsupervised models. I think this is just a really nice way of carving up problems into where you have data, but also where you need to insert optimization to make things work well. They also have the very important problem of figuring out exactly what we think the reward function should be, to what extent human choices are actually a good indicator of human preferences. So on that note, let's go get some coffee. Come back and I want to say a half an hour. Can we? Half an hour. And thank you all for your attention.